and Daogu. Today, I'll be presenting tightly secure inner product functional encryption, revisited, compact, lattice-based, and more. First, let me recall the notion of provable security. It means we reduce the security of a scheme to the harness of an underlying problem. In other words, if an adversary A can break the scheme, we can turn A into an adversary B that solves the hard problem. When TB approximates TA, we define the security loss L as the ratio epsilon A over epsilon B. If L equals 0.1, the reduction is tight. If L equals poly lambda, it is almost tight reduction. Accordingly, we say the scheme has tight or almost tight security. Next, let me reintroduce the semantics of inner product functional encryption, namely IPFE. Consider the following scenario. There is a DNA database and a user. The DNA database runs setup algorithms to generate MPK, MSK, and send MPK to the user. The user specifies an inner product operator via vector Y. Then the DNA database uses MSK and Y to run GEN algorithm, obtaining the functional key SKY. After receiving SKY, for any ciphertext of a vector X, the user runs functional decryption algorithms with SKY to recover only the inner product of vector X and vector Y. Beyond this, nothing of X is revealed. In this work, we focus on IND-CPA security for IPFE. In a security experiment, the challenger runs setup algorithm, flips a bit B and sends MPK to the adversary. The adversary may query a functional key oracle on vector yi and receives the corresponding functional keys skyi. It submits the pair x0j, x1j to the encryption oracle and receives the challenge ciphertext of xbj. The adversary may interleave these two types of queries. Finally, the adversary outputs a guess B prime. If B equals B prime with non-negligible advantage, the adversary wins. To rule out trivial attacks, we require that the inner product x0j yi and x1j yi are equal for all ij. If no PPT adversary can win with non-negligible advantage, we say the IPFE scheme satisfies IND-CPA security. Note that while tightly preserving transformations, we can derive more tightly secure schemes from tightly IND-CPA secure IPFE. Therefore, designing tightly IND-CPA secure IPFE schemes is a fundamental and worthwhile. To date, the most efficient IPFE schemes are due to AIS 16, and all tightly secure IPFE schemes stem from Tomida 19. However, the number of encryption keys might be very large. As noted in Tomida 19, in DNA analysis, M approximate 2 to the power of 13 and Q approximate 2 to the power of 27. In such cases, Tomida 19 leads to a large ciphertext. So Tomida asked, can we construct more compact secure IPFE schemes? Another natural problem is, can we build tightly secure IPFE from other assumptions such as LW or DCR? We answer both questions in the affirmative. Our first contribution is a more compact and tightly secure IPFE. Compared with the high expansion rate of Tomida 19 and the large security loss of AL16. Our schemes strike a better balance. Specifically, our constructions are parameterized by a constant L, allowing us to tune the trade-off between security loss and expansion rate. For example, setting L equals 100 yields ciphertext expansion about 1.02 and a constant security loss around 300. Even after compensating log L bits security loss, our communication cost remains noticeably better than Tomida 19. In short, this resolves Tomida's problem. Our second contribution is first, tightly secure IPFE from DCR or LW assumptions. We achieve this by proposing a new technical tool, two-level inner product hash proof system. TLIP HPS can be instantiated under the DDH, DCR, or LW assumptions, and it yields a generic construction from TLIP HPS to tightly secure IPFE. This unified framework leads to more compact DDH-based tightly secure IPFE, and the first DCR-based tightly secure IPFE, the first LWE-based tightly secure IPFE. As a byproduct, our framework gives a tighter security for ALS IPFE scheme by setting L equals M, which reduces the security loss of AL16 from OQ to OM. Now, let me briefly recap some classic IPFE construction paradigm. Firstly, let's recall the ALS scheme. It uses an M by 2 matrix K as the master secret key. The public key is AKA. For vector Y, the functional key is SKY equals Y transpose times K. To encrypt a vector X, the ciphertext is AW, KAW plus X. The security proof first relies on the DDH assumption, replacing AW with a uniform random vector. Then gets delta X, namely X0 minus X1, and observing the only information leaking about K is through KA and Y transpose K. Hence, we can replace K with K plus delta X times A per. Then it results in adding an extra term in the ciphertext, delta X times A per times uniform, namely delta X times a uniform value. By a standard statistic argument, the security holds. However, this strategy works only in the single ciphertext setting. To obtain tight security in the multi-challenge ciphertext setting, Tomida introduced into M copies K matrix. This method achieves tightness but incurs high ciphertext expansion and large MSK and PK. Moreover, it is unclear how to extend this method to other assumptions beyond DDH assumption. So, can we reduce the ciphertext size and generalize to other assumptions? To address these issues, we abstract both ALS and Tomida schemes and introduce a new technical tool called two-level inner product hash proof system, TLIP-HPS. Hash proof system was introduced by Kramer and Shoup. HPS is associated with an MP language L. The universe is X that has a hard subset membership problem and a hash family lambda indexed by a secret key SK. There are two ways to compute a hash value. With SK, we can use a private evaluation pre to compute the hash value for any C in the set X. Alternatively, project SK to PK. We can also use a public evaluation pub with a witness W to compute the same hash value for any C in the set L. The two ways are equivalent for any element in the subset L. Compared with traditional HPS, our TLIP HPS has two levels. The out level is a new variant of HPS called inner product HPS, which supports computations of inner products of hash values, namely the mapping from the set pi to the set G. We also introduced the functional key generation function view to derive functional keys fky and the function private evaluation algorithm fpri to compute the inner product of lambda c and y use fky. The outer IPHPS lambda is paired with an inner cohash function gamma. The remaining entropy of SK triggers the cohash. The cohash is a keyed hash function, mapping the set X to the set G. The outer level IPHPS satisfies completeness properties. Correctness assures that two ways to compute the hash value call inside the for C belongs to L. Functional correctness ensures that two ways to compute the inner product of hash value and the vector Y call inside. Except for completeness, IPHPS has a subset membership problem as usual. We omit it here. Inner cohash satisfies functional smoothness properties. As for SK, in the presence of both PK and multiple functional keys FKY, when evaluating the hash family of Ci in the set X, the remaining entropy of SK triggers the inner cone hash values gamma Ci for any tilde X orthogonal to all queries Yi. The distribution of hash value is statistical indistinguishable from the distribution with an added term gamma Ci times tilde X. The multi-key extracting property of the cohash further guarantees the randomness of multiple cone hash values. For example, if the cohash behaves like an inner product function, the values can be tightly amplified to independent uniform randomness. That is, we can first trigger cohash and then amplify to uniform randomness. The tight amplification is what we call multi-key extracting. Now I'll show a generic construction of tightly secure IPFE from TL IPHPS. The generic construction is parameterized by a chosen constant L. Let tilde m equals the ratio m over L. We use tilde m copies to build the scheme. The encryption algorithms uses the public evaluation pub on tilde m copies of TL IPHPS to obtain the hash values of Ci, and sum them to mask the message vector X. The ciphertext has two parts. The first part contains the language instances, and the second part is the masking term. The key generation algorithms use the functional key generation function on tilde m copies of tilde IPHPS to obtain FKI1, which together form the IPFE functional key. The decryption algorithm takes SKY and CT as input, uses functional private evaluation fpri and the functional keys to compute the inner product of hash values and the vector Y. Then by linearity of inner product, subtracting this form, the masking terms yields the inner product of X and Y. Now, why does this compact design works well? Let me outline our cone proof strategies. Proof strategy 1, trigger cohash while functional smoothness. First, by correctness, we can switch public evaluation to private evaluation. Just like this, we avoid sampling from L with the witness W. Consider the fact a uniform distribution of Vj, which is spanned by delta x delta xj, suffice to mask the delta xj. So we hope to adaptively trigger cohash to form the vector subspace Vj for every j's query. We do preparation by switching language adaptively. Let dj denote the current dimension, namely the dimension of vj. We utilize the multi-MP to switch first dj language instances from the language L to the larger set X. With this in place, we can adaptively trigger cohash functions. By functional smoothness, we extract cohash terms gamma si Cij times delta xi star, where delta xi star is the basis of Vj. Since each yi is orthogonal to the Vj, this application is valid. Strategy 2. Amplification via multi-key extracting of cohash. This lets us amplify these cohash terms into uniform random values, just like this. As a result, we obtain independent random terms. If dj is equal or smaller than tilde m, then these random terms form a uniform distribution over vj, which suffices to mask the j's challenging message xbj. But what if dj is bigger than tilde m? Here comes our proof strategy 3, iterative language switching. Without loss of generality, suppose dj is equal or bigger than k times tilde m and smaller than k plus 1 times tilde m. Then in the first round of language switching by proof strategy 1 and 2, we obtain tilde m linearly independent random terms from delta x1 star to delta x tilde x m star. In the second round of language switching via proof strategy I and 2, it has the same effect and we obtain extra tilde m linearly independent random terms. From delta x tilde m plus 1 star to delta x 2 times tilde m star. Iteratively do this. In the k plus 1 round, we obtain the last dj minus k times my tilde m linearly independent random terms. Notice that it is exactly the uniform distribution over Vj. Namely, after k plus 1 round, we extract enough entropy to hide xbj, then complete our security proof. Finally, let me discuss how to instantiate TL-IP-HPS from LW assumption. LW assumption naturally does not result in exact evaluation, so we need adapting TL-IP-HPS to allow approximate evaluation. We move from a deterministic TL-IP-HPS to a probabilistic TL-IP-HPS. We replace the correctness with statistic valuation indistinguishability. Keep functional correctness the same. Make deterministic cohash pub probabilistic, and keep functional smoothly unchanged. Then under these modifications, we can construct TL-IP-HPS from LWE, like this. We can verify these properties one by one. For example, we use margin lemma to prove the statistic evaluation indistinguishability. To conclude, in this work, we give a unified framework for tightly secure IPFE from TL-IP-HPS, armed with our compact design and economic proof strategy. We obtain more compact, tightly secure DDH-based IPFE, solving Tomida's problem. We obtain the first tightly secure DCR-based IPFE. We obtain the first tightly secure IOWE-based IPFE. As a byproduct, the framework uses tighter security laws for AL16, as illustrated on the right. A further interesting problem is whether even better IPFE schemes exist under this trade-off curve. That's all. Thank you for your attention.
All right. Thank you very much for coming to the session.